So for the second part, I'm going to talk about essentially a way of understanding the clusters of solutions, and then how you can do computations based on that, and the progress we've made in trying to prove some of those predictions. Okay, so the first thing is, a good viewpoint to take is to think about what a random solution looks like. So you have your graph. It was chosen randomly, but given the graph, we can talk about what does a random coloring of this graph looks like, and about the probability distribution of the random graph. And in particular for coloring, we can write the probability of a coloring in a nice form, which is just by a product of local interactions. And these local interactions just say, on each of the edges, the endpoint, you have the indicator that the endpoints are different colors. And then there's a normalizing constant, z, which we'll call the partition function, but in this case, it's just the number of colorings of the graph, what we were computing expected values of before. Okay, and this is just a sort of a special case. Oh, no, actually, I wanted to say, and we're going to be particularly interested in thinking about these sorts of models on trees. The random graphs we'll look at are not trees. They'll have lots of cycles, but almost all of the cycles will be very big cycles. You don't of sort of length, at least log n. There'll be very few small cycles of the graph. So the graphs are locally tree-like in the sense that if you pick a random vertex in the graph, look at a ball of a constant radius around it, what you'll see is a tree. So we're going to look at sort of colorings and other models just on trees. I should say that writing the coloring as a sort of probability distribution given by a product of weights, this puts it in a sort of much bigger category of models of different sort of spin systems that you can write as probability distributions, where you have sort of some product of weights over the states and the vertices, and some product of weights over pairs of vertices on edges. Something like, this includes things like the famous easing model, but all of the random constraint satisfaction problems that we'll look at can be sort of written in this form. And we're also going to look at sort of weighted versions of those models, and so that will be so having a more general framework will be useful for that. Okay. So if we're looking at trees, it turns out you can calculate many quantities on trees in a very sort of efficient way computationally using an algorithm called belief propagation, which will just be, it's basically just a sort of dynamic programming. And so it's a message passing algorithm, and the messages will be so each vertex will send a message to its neighbor, so a message from U to V. The vertex U will tell V what probability it thinks its marginal probabilities are in the graph, where the graph is the tree minus the edge from U to V. So it's like you saying, if I ignore the effect of the edge connecting to V, what should my marginal distribution be? And so in this case, let's think of this as a coloring on this tree, but okay, then just by symmetry, all the marginals will be 1 over 3. So let's pretend, let's sort of fix a boundary condition on the leaves. So then the probability of U in this tree here, well, it's next to only green variables, so it's equally likely to be blue or red. So the probability is, its marginal would be a half, 0. And that's the message it sends to V. And we could compute the other messages on the other vertices. And now the useful thing about belief propagation is that you can do it iteratively. So suppose we wanted the message from V down to its neighbor on the right. Now this is more complicated because it's a depth 2 tree. Okay, it's not very complicated, but it's okay. But you can. The idea of belief propagation is you can, within this tree, you can combine the incoming messages to V to give you the outgoing message to its other neighbor. And so it will just be this formula here, and it's a formula in terms of the incoming messages to you on, well, okay, I've written it as a sort of general formula, so the message from U to V can be written in terms of the other incoming messages from into U. And it's essentially just the probability that, so if you removed V, it's the probability that, so the probability, or the mass that it puts on red would be the probability that neither of these are red, normalized to be a probability distribution. Okay, so that's, so you could then iteratively calculate all of the messages in the tree this way. And if you did that, you could work out lots of things. In particular, you could work out, say, what the marginal distribution at the root or any of the vertices would be. It's enough just to know all the incoming messages into a vertex in order to calculate the marginal for it. You can also do this on general spin systems. So that, again, the message from U to V will be some function of all the other incoming messages to you. Another thing that you can do with these messages is calculate the partition function. So for colorings, it would be calculating the number of colorings of the tree. Again, in this example, not very complicated, but and you do it, but it has a nice simple form, and in particular a very local form. So you write down phi of V is essentially the change in the log partition function when you add in a vertex V. So if you think of the tree without the vertex V, and then you place the vertex V back in, how does that change the number of colorings? Well, it's sort of for each color you can say what's the probability that none of its neighbors were that color, add that up, and then take the log of that. Similarly, you can say what's the effect on the log partition function for adding in an edge, which will just be log of the probability that the endpoints of the edge were had different colors. And I've written this just for colorings, but but you can do this for any spin system in a similar sort of systematic way. And then the partition function on the tree is just a sum of these vertex terms minus a sum of the edge terms. And this holds on any tree. So it's a very simple formula. You might wonder why you add the vertex terms and subtract the edge terms. It's essentially because of a double counting phenomena. So when you add in a vertex, you also add in each of the edges that it's adjacent to. And so each edge, the effect of each edge is incorporated in both vertex terms that it's in. So if you, so since that's counted twice, you then need to subtract it off. Okay. So if you do belief propagation on the tree, you also have a simple formula for the partition function of the tree as well. And it's in terms of very local quantities. It's just in terms of the messages either incoming into the vertex or for edges, the two messages along the edge. Okay. So what's useful about having these belief propagation equations? It turns out that these are a wonderful way of describing the clusters. So yeah, so you know, if we had just a general graph, it's locally tree-like, but it's not a tree. But we could still write down the same set of belief propagation equations and look for sets of messages that satisfy them. On a tree, that will be there'll be just a single unique way of solution to this system of equations. On a graph, there may be many solutions to this set of equations. And the thing is, for at least the class of models that we've been talking to, solutions to this set of BP equations are basically, or basically every cluster corresponds to some solution of the BP equations. So so we can sort of encode the cluster. So before, when I told you what a cluster was, it was sort of a connected component of solutions. Not a very tractable definition, just talking about adjacency of different solutions. It doesn't give you any way of calculating anything. Here, I'm saying that if you have one cluster of solutions, then you can sort of, from that, get a solution, like a solution for these equations. And when you have different clusters, you'll get different solutions. Okay. But now, this is sort of a set of variables. They live on the half edges of the graph, or like, I mean, on the directed edges of the graph, I should say. And they have to solve some equations, so they have to satisfy some constraints. So these BP equations are themselves a constraint satisfaction problem. So far what we've done is we started off with a constraint satisfaction problem like colorings, and then constructed a new, much more complicated looking constraint satisfaction problem, which doesn't sound like we're making any progress. It sounds like you're just making the problem more complicated. But there are some advantages. The first advantage is, remember we said when we're in the 1 RSB regime, we have clustering of solutions, but we don't see clusters of clusters or clusters of clusters of clusters. There's no extra structure. The solutions to this belief propagation CSP are the clusters themselves. So the solutions to this problem do not have clustering. So they're very rigid. If you have one solution, you don't expect to see any nearby ones. So you could then hope that you could apply the second moment method, and it would just work all the way up to the threshold. And indeed, in some cases, you can show that that's really the case. Another objection you might have to this being a sensible thing to do is that our original CSP, something like coloring, the set of states of each variable was discrete, one of Q colors. Here, the set of the states that the variables can take are a measure over Q colors. So it's continuous. How can you sort of combinatorially count something like that? It turns out that what you can show is that in the most interesting regimes, most of the measures that you get will be point masses, at least for some of the problems that we'll look at. So it's still a sensible thing to try and count these solutions, because although they're continuous objects, you can essentially project them to something that's discrete. So this is the plan. Count solutions to the BP equations as a proxy for clusters, and use that to determine where the satisfiability threshold occurs. If we want to know about the other transitions, we want to also know how many solutions there are in clusters. But if we assume that the tree formula also applies on our locally tree-like graphs, then it would also give you a natural way of saying what the weight of a cluster should be in terms of lots of local, in terms just of local quantities. So you just end up with a sort of rather complicated, but still just a weighted spin system that you can try and analyze. Okay. And okay. So at this point, I want to describe the physics predictions for the different thresholds, how they come up with those, and why they think that there's sort of this, condensation regime where it starts becoming 1 RSB. And I want to do it in the context of, say, things like models on a random regular graph rather than an Erdős-Renyi random graph because, well, for some technical reasons that, I don't want to get into. Okay, so this is a presentation for the next few slides on the predictions from physics. So we start off with a sort of an assumption, which is that if we look at the number of clusters of size e to the ns, that this will be given by, the expected number will be e to the n times sigma of s for some function sigma. So we'll assume that such a function exists. Okay, and then do calculations around that. So if we knew that, we could look at the expected value in terms of by just summing over clusters of different sizes. This is the number of solutions in a cluster of size e to the ns, well, it's e to the ns, and then the number of those you expect to see will be e to the n sigma of s. Since this is on an exponential scale, the biggest contribution is going to just come from the largest value of the exponent, so we're just maximizing s plus sigma of s. Okay? For this function sigma that we haven't proved that it exists, and we also don't know what it is. But we're interested in maximizing s plus sigma of s, and so the picture is, and so equivalently, that's the point at which the derivative of sigma will be minus 1. This is what the picture should look like in the clustered regime. As you increase the density of constraints, there'll be fewer clusters of solutions, so sigma will decrease. The condensation threshold should correspond to the point at which this lies on the tangent point lies on the axis. As we increase alpha more, in the condensation regime, the tangent point is strictly below the axis. The satisfiability threshold will be the last point at which you have any clusters of all, so the point at which the maximum of sigma is 0. And then in the unsatisfiable regime, sigma will just always be negative. Okay, so why do we expect this sort of change? Well, let's focus on what's happening in the condensation regime. So the tangent point gives you a negative value of sigma. What that corresponds to is clusters of that size are exponentially unlikely to occur. So in any, so you're very unlikely to see a cluster of that size. But still, we've just said that those are the ones that make the dominant contribution to the expected value. And as a consequence, the typical number of solutions will be much smaller than the expected value. The expected value will be dominated by very rare clusters that you don't expect to see. Okay, so what should you predict for the value of for the typical value? Well, the simplest prediction you could make would be that we'll take the biggest size cluster that actually appears. That will be the point at which the biggest root of sigma. And now at that point, sigma equals 0. So the number of clusters that you expect to see of that size will just be e to the n times 0, or just order 1. And so that's precisely the reason why you expect that most of the mass is on just a constant number of clusters. If you make a more sort of ambitious assumption that sigma doesn't just tell you the expected number of clusters on a particular scale, it also encodes like a Poisson density, sort of a random point process with a particular density, then that would lead you to the prediction that you should see a Poisson-Dirichlet distribution for the cluster sizes. Okay, so just to summarize, so you can write down a formula for the condensation regime, the condensation threshold. This is known for, so this has been proved in the case of Q colorings on random graphs when Q is large, and also in the regular nodal equal sat model. The most complicated phase is in the condensation regime, and this is where you can get, where the physics predictions gives you a prediction of the free energy, sort of the number of solutions in your typical CSP, and we only know this in the case of the regular nodal equal sat model. The satisfiability threshold is actually is the easiest of the three to do proofs for, and there are now sort of 4 different models in which this has been established. Okay, so those are the predictions. Of course, you don't know what sigma is, so how can you say something about that? The idea will be to build a spin system whose states are the clusters, or more precisely the solutions to the BP equations. And we said that we could have weights for those, and we're going to weight it according to the number of solutions to the power of lambda for some lambda between 0 and 1, which initially doesn't sound like a very desirable thing to do, because how are you going to count something when you're raising it to a non-integer power? But actually, you can write the weights in terms. So you can make this a weighted spin system, where the weights are like e to the lambda times phi, and on the vertices, and e to the minus lambda times phi on the edges, and these are all local quantities. So you can write down a spin system whose partition function z lambda will just be the sum over all the clusters of their weight to the power of lambda. And now, if you took z lambda, took its expected value, and it's the log of that, and then divided by n, then the biggest contribution will come from when s lambda plus sigma of s is maximized. So pretty much, you can think of this as just taking the Legendre transform of sigma s. So you can build a spin system, calculate its, or at least try and calculate the expected partition function. And if you can do that for all the values of lambda, you'll get the Legendre transform of sigma, so you can sort of, and then back sigma out of that, and then make all the predictions that you want to. This full system or program of understanding everything throughout the condensation regime has only been done for one particular model, the regular nodal equal sat model. But if you're just interested in the satisfiability threshold, then things are much simpler. For that, you just want to know, are there any clusters at all, which just corresponds to looking at unweighted clusters. So you don't need to, so it's like the case of lambda equals 0, you don't need to add any weights at all. And then things become a lot simpler. Okay, so in order to carry this out, we'd need to be able to compute moments for these complicated spin systems that we create. So how do you take moment? So we have a spin system And let's say we're doing this on a random deregular graph. How do we compute the expected partition function? Well, it's good to define the edge empirical distribution, which is just sort of what fraction of hxy will just be what fraction of edges have x on one side and y on the other. So it's just sort of saying what are the relative frequencies that you see on different edges. So we define this, and you could also define the vertex one. And we want to see in the expectation what sort of edge empirical distributions make the biggest contribution. And okay, so you can compute that by just calculating how many pairs of graphs and configurations on the graph that have a particular edge empirical distribution. So you can assign the states or colors to the vertices according to the vertex empirical distribution, which is just a function of the edge empirical distribution. And then for each edge, this is just going to, okay, it's not a very good picture because it will be a one regular graph, which is not a, but for each edge, we can then say what color is it going to be connected to on the other side. So we can count how many ways there are of doing each of these steps, and then we take a perfect matching or choose a matching that's compatible with the coloring. And you can write down in terms of lots of multinomials and factorials just the total number of ways of doing all of that. So it's counting graphs and with configurations on them where the configuration has a particular edge empirical distribution H. Okay? And now there's lots of factorials, so if you apply Stirling's formula a billion times, you can rewrite it and say that the contribution from edge empirical distribution H, I'll write this as, after we've taken the normalized log of it, I'll write it as phi of H, but this can be written as this formula here. It's not a very nice formula in general because first of all, it's quite high dimensional, and secondly, it's not convex or concave because you've got a difference of two entropy functions there. So the point will be you want to maximize this function, and it can have multiple maximizers. So how do you do that? Well, it turns out, so belief propagation will come in again. It turns out you can describe the maximizers of this function in terms of fixed points of the BP equation, sort of m equals BP of m. Then the maximizers, or in actually any stationary point of phi of h, is of the form hxx prime is mx prime times psi of xx prime. This is sort of the weight on the edge. So this is the probability, the empirical distribution you'd expect to see on this edge in a tree where all of the messages were n. So there's a couple of proofs of this, and actually they're both in the set of notes. One is just by enough calculus, and the other is by essentially a resampling argument, which and they're both in the notes. So how am I going for time? Well, the resampling argument is essentially saying that you pick a small fraction of the vertices W, delete the edges from them and forget the spins, and then resample according to the weighted distribution, but with new connections of edges and new colors. Okay. And you want to see how the distribution changes as a result of doing that. If you were originally at the global maximizer, then this operation should be essentially exchangeable. So it shouldn't change the distribution at all. And well, okay, you can show that the edge empirical distribution has to be of the form that I said. So you have to find a fixed point of the BP equations. Okay, so yeah, sorry, shouldn't have gone through that so quickly, but basically the idea is if you can solve these belief propagation equations, then you can compute the moments of the partition function and then hopefully do the second moment method. So let's see this in action for the maximal independent set of a random regular graph. I guess my picture is not really a regular graph, but we'll be talking about this for a random D-regular graph, and where D is a very big constant, say. Okay, so the first thing you might think of doing is to just look at what's called the hardcore model, which is a probability distribution over independent sets. But it's weighted by lambda to the power of the size of the independent set. So if you make lambda really big, that will put a lot of mass on the biggest independent sets of the graph. But if you make lambda too big, you'll end up sort of biasing things towards, or make lambda really big and then compute the partition function, you end up biasing it towards graphs with really big independent sets. The biggest case of which would be if you just had a random bipartite graph. Okay, so you can't do something just as simple as take lambda to infinity in this model and weight and sort of set the weight so that you have all the mass on the biggest independent sets. Again, because of the existence of rare graphs that have much bigger maximal independent sets. So instead, we can look at the belief propagation equations. So remember, with the belief propagation equations, you have a measure over the states. In this case, the states are just 0 or 1, so we could think of it as just m will just be the marginal of 1. And then you can, it's simple to just write down the BP equation for this. But now imagine in the BP equations we took lambda to infinity. You get something very simple, what I'll call sort of the warning propagation messages, which are, so all of the state will, so you'll get a 1 if all of the incoming messages are 0, and a 0 otherwise. So all of the warning propagation messages will just be 0s or 1s. And so the great thing about that is that now rather than having to deal with sort of a constraint satisfaction problem whose states are, lying in the interval from 0, 1, now the states are just either 0 or 1. So every directed edge of the graph will have a label that's either 0 or 1. And the rule is that at each vertex, an outgoing message or edge has a 1 if and only if all of the other incoming messages to that one are 0. Okay, so what's this got to do with the big independent sets in the graph? So what we call the frozen model will be sort of given by the sort of warning propagation configuration. So if these black numbers represent the sort of upgoing messages, we can sort of calculate. So this is a 0 because it has an incoming 1, whereas this is a 1 because all of the incoming messages are 0. And then, so this is all the messages going up the tree, but you can also work out the messages going down the tree. Okay. And what you find is you get 3 different types of vertices, which I'll call 0, 1, and free. And what they correspond to is essentially groups of locally maximal independent sets. So and within this group, if a vertex is labeled as 0, that will mean that that vertex is definitely not in the independent set. And something will be called a zero vertex if it has at least 2 incoming 1 messages to it. And so all the outgoing messages are 0. On the other hand, it will be called a 1 if all the outgoing messages are 1. Equivalently, there's only incoming messages are 0. And that will mean definitely in the independent set. And then there's an intermediate case where you have at least exactly 1 incoming 1. And then there's 1, and then on the same edge, there's an outgoing 1 because all of the other incoming messages were 0. So, and these are what we call the free vertices. They come in pairs. They correspond to the edges where you have a 1 going in both directions on the edge. So we classify vertices as either 0, 1, or free. And so how do you build an independent set out of this? Well, for each of the 1 vertices, you'll choose, that will be in the independent set. And for each of the pairs of free variables, one of those 2 vertices will be in the independent set. And what you need to show is that the free variables are sort of sparse enough that you can if you have a pair of neighboring vertices that are a pair of free variables, of course they're next to each other, so only one of them can be in the independent set. But you want to show that actually you can find a configuration where you choose for every pair of free variables, one of them gets chosen, and that's something that you'll be able to do at least if D is big enough. So we write the size of the independent set. So we'll get this frozen model configuration from the warning propagation messages. And then the size of the independent set will just be the number of 1s plus half the number of frees. And that's something that we could write in terms of the edge empirical distribution. So how do we count that? So we want to count clusters, or these warning propagation configurations that have size at least, or let's say exactly alpha n. So we want to maximize this function phi, but do it in the restricted case where such that the size the density of the independent set corresponds to alpha. So it's a maximization problem, but in a restricted setting. So how do you do sort of constrained optimization? You can add Lagrange multipliers. So if we have a maximizer, we can then sort of add in a weight such that to the function that will make it a sort of like a real maximizer. And so what does adding in this weight do? Well, the function phi gets modified by adding in this sort of theta term in the interaction here. And basically what the effect of that's going to be is just we've created a new spin system with except where the configurations are weighted. And so the weight is basically theta to the power of the size of the independent set. Okay? So you have this, so we now have these weighted spin systems. And so we want to calculate the expected number you see of these. So so you solve the belief propagation equation. So for each value of theta, there will be a sort of Q, and Q is going to correspond to the probability of a message being 1. For each value, so for a particular theta, you have this weighted model, and it will correspond. And for each theta, there will be a particular density of the independent set you get out of that. And for each theta, you can also write down phi, which will be the partition function for that model. And then you find so you want to look at the largest value of theta, which will correspond to the largest value of alpha, for which you actually see independent sets of that size. And so you you find the root of this equation, and then plug that into, and then this will be the formula. So alpha star equals this. And this is the one RSB prediction for the size of the largest independent set. So and so it just comes from counting these warning propagation configurations. Okay, so if we want to show that we actually have those those configurations, we need to do the second moment. There's a more complicated belief propagation equation for that. And what you show is that there's two solutions. One that corresponds to seeing essentially two independent-looking configurations, and another fixed point that corresponds to two completely identical configurations. And what's important is that these belief propagation or warning propagation configurations are very rigid. If you have one solution, you don't see any other ones that are close by to it. And it's really that property that means that the second moment method will work, because there'll be, when you do this, when you look at the second moment, there'll be sort of a contribution from two fixed points, one that corresponds to independent-looking pairs of solutions, and this will give you the first moment squared, and another that corresponds to just pairs of completely identical ones, and this will give you just the first moment. But if the first moment is, tending to infinity, then the first moment squared will be bigger than the first moment, and so the main contribution will come from the independent copies case, and then the second moment method will work. And so whenever when D is large enough, whenever this phi of theta is greater than 0, you can apply the second moment method. So it works all the way down to the threshold. You can get an upper bound. You can either do it directly, or a sort of version of the interpolation method also can give the correct upper bound. And so showed that for all sufficiently large D, you can the one RSB prediction is true. So you can work out the first order term, was the formula from a couple of slides ago. If you work a bit harder, you can give even more precise estimates. There's a logarithmic correction, and then after that, there's random fluctuations in the size of the biggest independent set, but the fluctuations are tiny. So in particular, the fluctuations are of bounded size. They don't tend to infinity with the size of the graph. So in random regular graphs, the size of the maximal independent set is very concentrated. For Erdős-Renyi random graphs, it would be much less concentrated. You'd have square root n fluctuations. So our proof was only for D large enough. This is, partly our shortcoming, because just in a sense, everything becomes much more concentrated when the degree is large. So it's substantially easier to work with in that case. But actually, if you look at what the physicists say, this prediction should only hold down to D equals 20. For D equals 19 down to D equals 3, there's this prediction is supposed to be an overestimate, and it's no longer in the 1 RSB universality class. It's in a more complicated universality class. It's supposed to be full replica symmetry breaking, which sort of means that if you take, say, two random solutions, the overlap Like there's a continuum of different overlap values or like Hamming distance values you could get. So it becomes much and substantially more complicated, and I think even the physicists don't have a formula that they could just write down in the case of D less than or equal to 19. So that's really a whole much more complicated horizon that we don't understand so well. Let me, okay. Maybe this is a good time to finish off. I've just, yeah, so anyway, thanks for listening. Okay, so come. Okay, so you have in the frozen model configuration. There's most of the variables will be 0, and then there'll be a few ones that are 1, and then we get these sort of pairs of free variables. And you could then have another free variable next to that, and sort of a long chain of these. And then you want to, and so if the prediction is going to be correct, you want to be able to, so there'll be some other free variables here. You want to be able to assign all of the free variables in a sort of, no, okay, you want to be able to assign half of the free variables to be 1 if the prediction is going to be right. And for that, you need that the free variables are sort of sparse enough so that they're in a certain way subcritical. So they'll sort of look like a branching process, and you want that branching process to be subcritical. And if you do the computation when D is 19 or smaller, you get a supercritical branching process, and you can't assign all the and actually you can think of these free variables as being like these which one of the pairs of free variables you choose to be in the independent set as essentially a 2-sat formula. And for 2-sat, I didn't say, but for random 2-sat, it's actually much simpler. There's the critical density is just 1. This was worked out in the early 90s, and it's just a branching process argument. And essentially, so within these maximal independent sets, you have to solve what's equivalent to a 2-sat formula, and it essentially boils down to when that's satisfiable or not. So as D gets bigger, the maximal independent sets become more rigid, there's fewer free variables, and the threshold for where that happens to be 20. By contrast, for the random k-sat problem, there it's supposed to be 1 RSB all the way down to k equals 3. And actually, even the method of proof could potentially work down to k equals 3. There's no clear sort of reason why that would have to fail. On the other hand, there are when D is bigger or k is bigger, lots of quantities just become much more concentrated. And so in, say, the random k-sat model, if you look at a particular vertex, you could say, what's the probability that will be true in a random formula? And it won't be a half because like it depends on how many times it's negated or not negated. But when k is big, the sort of empirical distribution of those is very concentrated around a half. But if you can compute what it should be when, and even for k equals 4, it still looks like a very nice peak. For k equals 3, it's sort of, I mean, it's biggest in the middle, but it looks like a density of just a spread out function. And so actually pushing the methods down all the way to k equals 3 looks exceedingly challenging.